it. All right, so am I sharing my screen? Yep. Okay, excellent. All right, so I've been playing with my toys. Okay, I have to confess, I've been playing with my toys, and this is actually still Joplin. I changed a few things. First of all, it's obvious that I'm using a dark theme. Just because everything else is almost everything else is in using the dark theme already, so might as well change this one to also use a dark theme. And two, I have been grading and entering the grades for the second exam. It's all entered onto my own spreadsheet, but I have not put all the scores onto Canvas yet. So that's next. Oh, okay, cool. I also changed the editor style, so it is actually using VI keystroke now. Yes, I know some people are going like, why would you want to do something like that? But that's just what I'm used to. So I changed everything to using VI keystrokes, including my browsers. Actually, using my browser, there's something called Vimium. Yeah, exam 2 grades will be entered into Canvas shortly after the class today. I got all the raw scores already. Um, I can probably just run the script and share everything that I have at this point. Um, yeah, maybe I can do that. Maybe later. Haven't quite decided yet. I think the class as a whole did pretty good in this particular exam. So nothing to worry about, for the most part for the class. All right, so getting back to the concept of graphs, right? So this is the kind of graph that I'm creating right now, and I'm trying to assign the distance values for the edges. Um, so here we have a whole bunch of question marks. So the first thing we need to do is to find out which ones are the destinations. So we'll just go ahead and designate E as our destination. So we'll say vertex where vertex E is the destination. So obviously you probably want to focus on the right hand side because I changed the font, and I'm using a much smaller font on the left hand side as I type the diagrams. It turns out to be working out pretty good, because it takes a little bit more space to type in the graph, using this particular format. All right, so now we want to find out, how we can test Dijkstra's algorithm. And Dijkstra's algorithm is interesting, well, at least the one that we talk about in this class is interesting in the sense that you can have multiple destinations, and it also finds, all the shortest paths from every single vertex to a destination all at the same time. So that part is different from the one that you either learned or you're going to learn from Iraj's CISP430. All right, so we have designated one particular destination cell, and then we are going to now we have to come up with the values. In other words, we have to find out what would make this interesting, right? What would make this interesting where we would have to update, okay, one particular vertex, at least one, is going to have to update itself and go like, okay, the first path that we found was actually not the shortest path, and now we have to update, certain things. So what we're going to do is to pretend, not pretend, but we already know, the destination vertex is vertex E. So if you have worked on the algorithm over the weekend, which I assume that you have, um, you already know that it works backwards. Okay, it starts with all the destinations, and then it goes back and say, okay, who is right next to a destination, who is only one edge away from a destination. So in this case, we can see vertex C and vertex D are both only one edge away from the destination, but there's no rule saying that this one edge here from going from C to E has to be less expensive compared to the two edges combined, going from C to D and then to E. So that's what we're going to do, is to force Dijkstra's algorithm to update values, because the first one that we found turned out not to be the best path. So we're going to give this one a pretty high value, let's say 10. And now we have to make sure that the path of C, D, and E is going to end up with a shorter, let's see, and I'm not going to call it distance, length. There we go. So CDE needs to have a shorter length compared to the distance of 10, which is the cost of one single edge going from C to E in this case. So there are many ways to make this happen, right? C to D, let's see, we can make this a 2, and then from D to E we can make that a 4. That will work. So I'm just going backwards, to generate all of these alternatives. Okay, so now we also have another scenario where we can do the same thing, because once we get to C, we will want to kind of trick Dijkstra's algorithm, okay? Because we want to try to trick the algorithm as much as we can, just to make sure that it will still do the right thing, even though we attempt to trick it. So this time, it is about going to vertex D. So now we want the first thing from B to D to be the longer, to have a larger distance value compared to the length going from B to C and then to D. We locked down this value already. It's a 2, so we can say B to D is a 10. Okay, so let's update B to D as a 10. B to D is right here. Change that to a 10. And then from B to C, we just have to make it 7 or less if we're only talking about integers, but it can be anything less than 8 if we do not want to restrict ourselves to integers, which is perfectly fine. Okay, we don't have to use integers in this case, so we'll just make it a 6. Okay, so from B to C, we are going to make it a 6 right there. All right, so now we're going to take a look at this particular configuration here. Okay, we have another configuration just like that. Okay, because when you look at C here, we want the first thing from A to C to be more expensive than A, B, and then to C. So this time we can make it barely worse. Okay, so from A to C we'll make it an 8, and then from A to B we'll make it a 1. There we go. And then we have this kind of mysterious edge going backwards. Okay, so we are basically having a loop. So we want to make sure Dijkstra's algorithm can handle a loop. And in this case, we'll make the loop or the distance of the edge that is contributing to the loop to be 0. Okay, so we will see whether Dijkstra's algorithm can handle all of these tricky situations. Do we have any questions about how the values are set up at this point? Or why I use these specific value, because I want to trick Dijkstra's algorithm as much as I can. All right, so we are not seeing any questions. All right, so what I think would be a good idea for you guys to do is to go to the notes by yourself. Okay, because this way I can then I don't need to display the algorithm in the area that is being recorded, and you guys can look at it on a separate window on your own desktop computer. So I'm going to copy and paste the link into Discord. So this way it's easy for you guys just to click on that link, and you can open a different browser window on the other side. So this way you don't have to, I don't have to flip-flop between the screens too much. So I'm going to pull this tab out and kind of put it on the side. I still need it, even though I know the algorithm already, because I want to direct you to certain lines of code as we go through the trace of this algorithm. All right, so getting back to Joplin. So Joplin is really here, just so that we can take notes. So the other thing that you can also do is to have another window to look at the graph itself. So because we are using Discord, it's super easy to do, because now I can just do a screen capture of just this portion over here. And then I can paste it into Discord, and you can now open up, you can right click on the image on Discord and then say open link. Okay, so that will open a separate window just to look at the graph itself. All right, so now that we have everything in place, we can start to work on the algorithm itself. All right, so when you look at the algorithm, we got a few things that we need to initialize. We have to be given the graph. So in this case, if you want to, okay, I'm going to show you a few items in it, but you're going to have to uh, finish it, okay, because I'm not going to spend too much time to look at the actual representation. So when we talk about a graph, it has two items in it as a two tuple. The first one would be the set of all the vertices. So I'm not even going to bother to use LaTeX because it doesn't need to be using LaTeX. So in this case, our set of vertices would be from A to E. So we have A, B, C, D, D, and E as the set of vertices, and then the set of edges is going to be a little bit more verbose because we got AB, uppercase, there we go. So we got AB as one edge, and then we got AC as one edge, and then we got CA as an edge. Remember, these edges are directed, and that's because a tuple is order dependent. So we're always going from the first element or element 0 to element 1, and so on. Okay, I'm not going to spend too much time in today's lecture just to show you what is going to be in the set of all the edges. All right. So if it is undirected, okay, so this is something we talked about last time, is if you want to represent a undirected graph using a directed graph, then you're going to have both of those edges. So if you want to express there's connectivity between A and C in a undirected graph, but the underlying representation is a directed graph, then you're going to have both tuples, AC and CA, to basically say that, okay, this is, even though, okay, from the perspective of a undirected graph, this is one single edge, it really is represented by two edges when the underlying representation is a digraph, which is the abbreviated form of directed graph, which is directional graph. All right, so with that question answered, all right, so this is given to us. The D function is also given to us, and it's also going to be very tedious because it has the same elements as the set of all edges. So in this case, we have AB, and the edge AB has a distance of 1, and then the second one is going to be, let's say, AC. So AC, oops, there we go, need extra parentheses. So AC is the edge, and then the distance of that edge is 8, and so on. So this one is also going to be quite tedious. So this is going to be, that's why the actual graphical representation is nice, because it's very concise, it's very intuitive. We just eyeball the whole thing and we can understand what it is. Yeah, it's very tedious, but it makes sense from the perspective of how do we write an algorithm to do this for us, right? Because when we are writing an algorithm, we cannot just say, hey, computer, just eyeball the whole thing and find out which one has the shortest path. That doesn't work. We wish that works, right? But it does not. So that's why, having the underlying representation using kind of the set notation is necessary, because we are trying to write an algorithm, or we're trying to verify the operation of an algorithm that can help us solve for all the shortest to solve for all the edges on all the shortest paths from every single vertex to a destination vertex. All right, so these are given to us. Okay, these two items are given to us. So is the set of S. Okay, S is a set of all the destination vertices. So in this case, we are only designating vertex E as a destination. So we only have E in here. Let's see, what else are we doing? All right, so the next item is for each. So when you are looking at the algorithm, the next item is saying, for each V in S, okay, so for each destination vertex, we want the L value to be 0. So now we have a choice, okay, we can choose how we want to represent the L values. For a graph like this, not too complex, we can have one column for each L value. You can also look at the L value as an actual function. So that part is kind of up to you. Okay, in a test, you can use either representation. So I'll give you an example of each one. Okay, so in this case, I do need to use LaTeX, because now we are using the set notations and whatnot. So you can look at the L, as a function, and the way it works is it maps from vertices to values, to real numbers. So it goes from the set of V, which is our domain, and then we have right arrow. Did I misspell? Nope. Right arrow is not misspelled, but it doesn't like it. Right arrow. Okay, maybe I just need something on the other side. Yep, I just need something on the other side. It just doesn't like to have empty spaces right before the dollar sign. So on the other side, we have R asterisk, which is basically all the non-negative real numbers. And obviously, these are, usually I use math BBR. And it's not in parentheses, it's supposed to be in braces to format that correctly. There we go. Alright, so this is the proper representation. If someone is bothered by the dark theme because it's not as easy to read, just let me know. I can switch it back to the light theme. Just let me know. Alright, so this is one way to look at R. And if this is how we want to look at R, then the elements of R is going, oh, L, sorry, yes. I look at L and then I say R. So if we want to look at it this way, if we want to look at L as a set, because that's one way to represent a function. So now we're looking at tuples, and in the tuple, the first thing has to come from the vertices. So we'll start with E because the initialization says, okay, let's initialize all the destination vertices first. So E is going to be associated with 0 because that's how we want to initialize the L value of all the vertices to just zeros. And then for everything else, they're all going to be mapped to infinity. So for everything else, so we'll start with A. A is going to be mapped to infinity, INFTY. There we go. And then same with B, same with C, same with D. So I just have to copy and paste this a few times. Not sure whether it will do a copy and paste because I'm in VI mode. Okay, it doesn't like that. Okay, I already tried to do the yanking thing in VI mode, and that doesn't work either. So it's not fully VI. It's just something. It has certain keystrokes recognized, but not everything. Backslash INFTY. There we go. All right. So this is one way to represent L, as a function. All right. So let me see if anyone has any questions at this point. Nope, we are not done. We are not even in the algorithm yet. So when in the algorithm, we're gonna have to update the value of L every time we change one of the L values. But we are not quite at that point yet. All right, can I explain what L is representing? So L is representing the length, okay, L for length, is representing the length of the shortest path known at this point from a vertex to a destination. Since we only got one destination, we all have to say, oh, okay, to that specific destination. But if we have multiple destinations, then it will be any destination that is quote unquote closest to that particular vertex. Alrighty. All right. And why is infinity used? It has to be a value where nothing is more than that. So infinity is one of those values. And the interesting thing is in IEEE double precision floating point numbers, there is actually a representation of quote unquote infinity. So you can actually assign the quote unquote value of infinity to a double type in C, C++, and just about any language that is using that representation. Alrighty, so are we good so far? Because I have just combined the two initializations, the two for each, into one single initialization, and this is the result of the initialization. Alrighty. Why not 0 rather than infinity? Because 1 is not 0, and it's easy to find a value that is greater than 1. Because we don't know, right? I mean, because we really don't know what is the length of a shortest path from a vertex to a destination. If the destination is not even reachable, then we want the L value to remain as infinity. It's sort of a placeholder, but it's not really exactly just a placeholder. It is just how we want to start the value as. Yeah, we want the shortest distance. So that's why we want to initialize this to infinity. So every time we find a shorter path, okay, every time we find a shorter path, we'll update the L value. Exactly. Jonathan W is correct. So we know we can't get longer than infinity. Exactly. You can get to the very last bit pattern that is less than infinity in a double, and that would still be less than infinity. So that's why we want to use the representation of infinity. It is actually, you can actually type in infinity as a constant in most programming languages because that particular bit pattern does exist. There is a way to represent infinity. But then you have to take CISP440 to learn that. From me. I'm not sure how other people teach it, but I do teach that concept in CISP440. All right. All right, so I think we are good here. And then we have one more thing to initialize, and that would be the set Q. So according to the algorithm, all we want Q to be is really just whatever S is. Okay, well, that's easy enough because in this case, the set S just has one single element, and since Q is initialized to have exactly the same value as S, it also has just one single element being E itself. So now we are done with all the initialization. Do we have any questions before we move on to the algorithm itself, which is starting with the while? All right. Q is representing the boundary of expansion because we're expanding from the destinations and backwards so that we can try to cover all of the vertices. And I'm not taking roll today. Today is the second last day that I can draw people. And I just decide, it doesn't really make any sense, for me at this point to try to help people to build up a habit to come to class. It's a little too late for that. Q is a set that keeps changing as we run the algorithm. The set S is given to us. So S is one of the parameters, and Q is a local variable, from the perspective of, actually turning this into code. I wouldn't call it a temporary variable. I would just call that a local variable that otherwise has no use outside of the algorithm. And you might ask, why don't we need Q outside of the algorithm? Well, let me ask you this question. How do we get out of the while loop? And if someone is asking, what while loop? I don't see any while loop on the screen. Well, remember, I told you guys to open up the algorithm on the side. I gave you the link. Look into that algorithm. Don't you see a while loop? And the question is, when the while loop exits, what is going to be the value of Q? And Aman is correct. It is going to be an empty set. So if you already know ahead of time when a particular variable is going to be an empty set when we are done with the subroutine, why would anyone care about the value of Q, knowing that it's always going to be an empty set after this subroutine is done with it? So that's why it is going to be a local variable, because a local variable is only visible from within the subroutine. So assuming the subroutine is going to implement the Dijkstra's algorithm, then no one else would need to know about the set Q. So there we go. Yep, the while loop stays while Q is non-empty, which means when we do exit from the loop, Q is going to be empty. Now, this is also a reason, okay, I know I'm digressing, but this is also a reason we do not use break in coding. Because if you start to use breaks and continue and all kinds of bad stuff, in an algorithm, the worst one is goto, okay? Because goto is really, really arbitrary. You can go to any label within the same subroutine. So this is why we don't do that, okay? Because I want to be able to just look at the condition of a loop and understand what it means to be staying in the loop and what it means to be exiting from the loop. Okay, because I don't want any break statement inside the loop that would say, here's another reason we can get out of the loop. So that is just, I think it's just a very bad idea. It's bad for documentation. It's also bad for debugging, because you can no longer make the assumption of, if I see the condition, I know what the condition is going to be after we get out of this loop, because it would just be a negation of the condition to stay in the loop. So as I said, it's a digression, but I believe this kind of digression is productive because we are in the context where the digression actually starts to make sense. Alrighty. So what are we going to do now? We are going to get into the loop. So this is where a table can come in handy, and the good thing is Joplin knows how to make a table. So we're going to make a table, and the way we make a table is to use the vertical bar as the vertical lines in the table, and then we just type in another vertical bar and so on. So now we have to think about how many things do we need to track. Well, there are a few things. Q is a set that we need to track. What else do we need to track? In the algorithm itself, we have a local variable called v, which is only useful when we are inside the while loop. So v is basically a local variable that is local to the scope of the body of the while loop itself, but it can also be local to the entire subroutine if you want to. But technically speaking, it only has to be local within the block of the loop itself. All right, so we got v. I'm just looking through the algorithm here. W is not, okay? W is not one of the variables that we need, because we only want to use W in the for all W thing in order to say, hey, we want to find the vertex that has the least L value. That's basically what W is useful for on that line. And then we have E, which is basically saying, we want to look at all the edges where V is the destination or the second element of the tuple. So from that perspective, that W is important, or we'll just say E in this case. All right, so yeah, I'm just looking at this, W, E are both important. So we'll have E and then a W here. All right, so what else do we need to track? We have E prime, which is a set that keeps track of the solution, of all the edges. And then we have one more thing, which is going to be our L values. So L needs to have its own column in this case. So that is how we're going to structure this. And I need to cheat a little bit here because I cannot remember exactly how to make a table. I know the vertical bar is important, but I also know that's not the only thing we need. So I'm going to look up my little cheat sheet here. Markdown guide from Joplin. And I'm looking up tables. Oh, okay, I see. So the next one is vertical bar, and then just using dashes to represent the line of a table. So it will also automatically turn the first row into boldface, because those are headers of each column. Now we just have to say, okay, what is the value of Q at this point? Well, Q is a set with E, uppercase E as an element in it. Okay, what about V? V doesn't really have a value yet, or it's not meaningful to talk about the value of V. What about E? We don't know yet. W, we don't know yet. E prime is initialized to be an empty set to begin with, and then L is what we have already stated. So L in this case is a set. E is going to infinity, and there's no easy way to type infinity, so I'm just going to use INF to represent infinity. Oh, E is 0, sorry. So the value of E, or the value associated with E, is 0, and then A to D are associated with infinity. So B is infinity, C goes to infinity, and then D also goes to infinity, and then one final vertical bar to end the whole thing. And let's see. Yep, that works. Okay, so this is a table. I know it's a little bit harder to see now because of the use of the dark theme. And as I said a little bit earlier, if you guys want me to switch back to the light theme, we can certainly do that. All right, so no comments about that. All right, that's fine. All right, so next thing we need to do is to go to the algorithm and say the first question is, can we get out? Can we just say that we are done? The answer is no, because Q is non-empty at this point. So we have to get into the algorithm. So the first thing we get into the algorithm is to find what V, or what vertex we should choose as V. So right now we only got one single element in the entire queue. So which one do you think is having the least L value of all the elements in Q? That was not a very smart question. I'm just checking to see whether you guys are actually paying attention or not. Yes. Can I say that again? No, because I have forgotten what I just said. Okay, but Jonathan is correct. E is going to be the value of V, which is a local variable at this point. We don't have an E yet, okay? So E does not exist, W does not exist, and L is the same way as before at this point. All right. So now we are going to update Q. So Q has to be updated as soon as we have chosen one vertex out of the set to quote-unquote process. We have to remove it from Q. So at this point, Q is going to be an empty set. Well, usually what I do is I kind of combine the two operations into one row, because they just kind of go along together. And then the next thing we need to do is to get to the for each statement. So the for each statement is a nested loop inside the while loop itself. So the for each statement is really just looking at every single element that meets that criteria that we have shown here. So when you look at the algorithm, it says here for each lowercase e is an element of a set, and that's basically an ad hoc set that we are creating right away. And the only thing that has to meet that particular requirement is in a tuple, we want the second item to be uppercase E. So we look up the graph, right? So we look at the graph, and once again, you can go to the screenshot of the graph, open it as it's in its own browser window. So that way you can just kind of focus on the graph itself. So we can see that there are two edges. One edge is DE, the other edge is CE. It doesn't matter which one you choose, okay? So there's no particular ordering when we choose an edge from the graph, where E, in this case uppercase E, is the second item of the tuple. The W is only locally used, just so that we can find the vertex with the least L value. So it's not explicitly represented. So that particular W on the first line, that says select V in the queue such that blah blah blah. So that for all W is used locally just to express the fact that we want to find the least. We want to find the vertex that has the least L value in this case. So that's why that W is not represented. All right. Okay, so now we're back to the graph itself, and we have two vertices. One is DE and the other one is CE. So I'm going to say pick DE first. So now we have nothing to say about Q because it stays the same as before, which is currently an empty set. V also has, we have nothing to say about V, but the lowercase e, which is representing which edge we want to look at, we are looking at DE as the edge at this point, and then that makes W vertex D, because D is vertex D is the first item of the two tuple, and then E prime is still empty at this point, and L is still the same as this point. All right, so let me just kind of pause here. Does everybody understand why lowercase e, which is a variable in the algorithm, is now having a value of vertex D and vertex E in it? Do we just carry the value in the table until it's changed? Yes, that is correct. So when you look at the table, if it is empty, if there's nothing in here, that means it is retaining a value from the last time we changed it. So this way I don't have to keep typing the same value over and over again, because the default is if a cell is empty, we just look up until we find something, and that would be the current value of a variable in the trace. It's kind of like a shorthand, just being lazy. Alrighty, and Jonathan W is typing something, so I'm gonna wait a little bit. Alright, so we're finding all connections to E. Okay, we're finding all the edges that lead to vertex E. That is correct. We're finding all not connections, because connections imply that it can be transitive, but we are looking at edges. We're looking edges where E is the second tuple of those edges. There we go, but we can only process one at a time. Okay, so basically this is an actual algorithm that you can run on. As soon as you have the notation of a set and the notation of a tuple, you can actually program this. All right, so in the algorithm, we are now down to the if statement. Okay, so the if statement has something to compute. So we have to compute the sum of L of V and D of E. So in this case, we can see V is E, and when we look up L, L of E is 0, and we want to add D of E to it. And when you look up the graph, D of E, D of the edge DE is 4. 0 plus 4 is 4. So we want to compare that to L of W. And when you look up the table, W is D. What is L of W at this point? Yes, uppercase E is a vertex. Lowercase e is a variable here. I really should not have used E as a as the name of an edge, because E is also representing the set of all the edges of the graph. So I apologize for overloading that particular name. But this E is kind of a string. Okay, it's just an identifier. All right. So the question is, when we evaluate the condition E, yes, E is a vertex. Uppercase E in this context is a vertex. So this is a this is a vertex. This is a vertex because of this thing here. This is our vertex E over here. Alrighty. Alright. Why can't we take the operator element of? I'm not sure where you're talking about. Okay, let me show you the algorithm here first. There we go. So in the algorithm, this lowercase e is an edge. Okay, it's a variable that is bound to one edge at a time. The requirement or the restriction of that edge is whatever the second item is has to be the variable v, but the variable v at this point has a value of uppercase E as an identifier of an element. So the other thing is I also unfortunately use E up here as the set of all the edges. So that's why it can be a little bit confusing. Yep. Okay. So when I'm talking, can I specify lowercase e, uppercase e? I can specify vertex e, the set e, and the variable e. Oh, this is great. Wait until you try to write a program where all the variable names are underscores. One single underscore, two underscores, three underscores, and so on. If you want to upset your CISP430 teacher, just do the program as usual and then start to replace the names of the variables and the functions to just underscores. You just have to make sure that they are a different number of underscores. Yep. That ought to get some attention right there. Yep. Not sure whether it's a good kind of attention or a bad kind of attention, but some attention for sure. All right, so getting back on the algorithm here. So we want to evaluate this condition, okay? L of V plus D of E, is it less than L of W? Okay, well, L of W, so let's check out what is L of V first. So we can see variable V has a value of vertex E, and we can also see D of E, D of edge, D of local variable, D of variable E. Variable E is DE, and then the D of DE is shown in the graph itself right here. So DE has a distance of 4, so that's what we're talking about. It is 4. So we are talking about this 0 plus 4, which is 4. What are we comparing it to? We're comparing that to L of W. So variable W has a value of D, which identifies vertex D, and vertex D is currently, L of D has a value of infinity at this point. And Jonathan is correct. 0 plus 4 is less than infinity, so the condition is true. So if the condition is true, then what do? We get into this bunch of statements here. So the first thing we do is, okay, let's update the L value of W so that it is actually what we used earlier for the computation, on the left-hand side of the less than, which is 4 in this case. So what I'm going to do is I'm just going to copy and paste. Okay, so all right, so we'll say there's no need to update Q, no need to update V, no need to update E, and no need to update W. And currently we have no need to update E prime either. And the only thing we want to update is the set representing the function L. So that's going to be this portion over here. So I'm just going to, oh, okay, that's not what I want. Alright, so let me see if I can do something like this. Does it truly understand VI commands? Yep, it does. I'm impressed. Alright, so this is not supposed to be here. And there we go. Alright, so we are supposed to be updating the L value of W, and W is D at this point. So that's why this particular infinity is now not infinity anymore. It is now 4. There you go. Yep, Jonathan W is correct. All right. So what else are we going to do? Well, the next thing we're going to do is to say, now this statement is a little bit more. It's too complex for what it's actually trying to do. It's basically saying if we already have an edge, if we already have edges, but we can actually only have up to 1. But if we already have an edge going from vertex W, we need to remove it, okay? In other words, if we already have an element in this particular set, okay, in E prime, that starts with vertex D, then we're going to have to remove that from E prime. Well, E prime is empty at this point, so there's nothing that we need to remove. So, okay, so that particular step doesn't do a single thing. In other words, this particular step here, for this particular instance, it's not going to do anything because we have an empty set of E prime at this point. There's nothing to remove from an empty set. And then Armand is typing. So we were just going through a particular vertex and checking shortest length away from it. Yes, so we now have an alternative path to a destination. That's what we have just discovered. Because in the context of this particular graph, okay, this specific graph, what we have said, what we are saying is, oh, guess what? We can get to a destination. In this case, vertex E, through E. I know that sounds stupid, but that's basically what we are saying is, vertex E knows how to get to a destination already. And for vertex E to get to a destination, the length is going to be 0. Now, since vertex D is going to vertex E, using an edge of 4, so now we can say, let's compare, okay? Let's find out what is the length of the shortest path from D to a destination right now. Oh, that's infinity, because we haven't explored anything going from D to a destination yet. Okay, so that's why the length of this current known path, shortest path to a destination from vertex D is infinity. But we have just discovered a new path. That path is going from D through E to a destination. Now, E being itself a destination doesn't matter. Okay, we just know that E can get to a destination. So the length of the path from E to a destination is 0 in this case, which means I can now say, I know at least there is a path from D to a destination with a length of 4. Now, is it going to be shorter than everything that we have found up to this point? I don't know. Okay, that's what the comparison is for. So that's why we have this comparison here. It is to determine whether we have just found a shorter path. Just because we found an alternative path does not mean it is shorter. All right. Yes, we're exactly going backwards. We're exactly going backwards, as I said earlier. Yep. Okay. So now, where are we up to? We are now up to this line here. We're going to make a union between E prime and a set of one single edge, which is between W and V, which is basically just the edge that we have talked about here. Okay, so in other words, when you look at this thing here, you can just replace it with lowercase e, which is a variable that we use to keep track of which edge are we talking about, going to, in this case, vertex E. So, so we're gonna update E prime. So let's go ahead and update. I have to go back to my Joplin window. Where is it? There we go. All right. So now we can update E prime. Okay. And I'm going to put it onto the same row over here, just because, everything inside each iteration of the for each loop, I'm just going to put everything into one single row. Okay. So E prime is no longer an empty set now because it has one single edge, which is to say, I know how to get from D to a destination now, and currently this is the shortest path. Going from D to E is the quickest way for vertex D to get to a destination. So you guys can focus over here instead of seeing what I type, but this is correct. Okay, so this is what we have at this point. Are we good so far? Now we are not done for what one iteration of the for loop is trying to do, but we are currently at this step here. Okay, we are just updating E prime. Are we good so far? All right, so now the next step is, we also need to make a change or update the set of Q, because now W is the boundary. Okay, the boundary is no longer vertex D, it is the boundary. We have moved the boundary of expansion to what W as a variable is containing, but what W is containing is just vertex D, so that's why we are also going to update Q. It is no longer an empty set, instead it has vertex D as an element in it at this point. Oof, okay, so are we doing okay? All right, cool. All right, so, but that's only one of the edges. We have two edges going to vertex E. One is the edge DE, and the other one is the edge CE. So now we're going to evaluate the edge CE. So we are just changing a few of the items here. And I totally messed up the Okay, let me just undo these operations. Paste again. And we want to replace that with a C. Replace that with a C. There we go. Now it looks good. Alright, so this is the second iteration of the for each loop. Now we need to evaluate the condition again. So which condition are we talking about? The condition of the conditional statement. So now we have to say, we're trying to find out, are we finding a shorter path from C to a destination? That's what we are asking. And to determine that, we are looking at what is the length of the shortest path from vertex Z to one of the destinations. Oh, that's pretty easy, because that's what the L value is supposed to tell us. So L of vertex Z is 0. Okay, we got that. Now we ask, what is the distance from C to E as a single edge? That turns out to be 10. 10 plus 0 is 10. And then we want to compare that 10, the value of 10, against L of C at this point. L of C is currently infinity. So we are really just asking, is 10 less than infinity? The answer is yes. So that means we have a whole bunch of updates again. But this time I'm just going to copy and paste a little bit here. So the first thing we do in the algorithm is to update the L value of C so it's no longer infinity and now it is 10. So that's how we update this value to be 10 right now. The second thing we do is to remove all the edges that start from vertex C in E prime. So we look up E prime, and E prime does not have anything that starts from vertex C, so there's nothing to remove. But we are going to have to add the new edge from C to E, because the edge C to E is the path from vertex C to one of the destinations. It's on the path of the shortest. Is on the shortest path from C to a destination. And then we also have one extra thing to do, which is to add vertex C to the set of Q, because vertex C is also a part of the quote-unquote frontier of the expansion of, okay, let's explore from the destination and backward to all of the other vertices. So now we have, so let me show you the graph first. So right now, vertex E is no longer at the border of the expansion or the boundary of the expansion. C and D are both on the boundary at this point. That concludes the for each loop, because the for each loop just wants to focus on vertex E and find out, okay, give me all the edges that are incoming to vertex E. So D is one of those edges, CE is one of those edges. Now that we have processed both of those incoming edges to vertex E, we are done with the for each loop, which will bring us all the way back to the while loop. The while loop is asking, is the set Q empty? Because if it is empty, we can get out of the loop. If it's not empty, we cannot get out of the loop. So when you look at the table here, Q is non-empty. It has 2 elements in it. So we cannot get out of the loop just yet. And then we have 2 elements this time. We have to find out which one has the least L value. The reason why we do that is because we're trying to be greedy. Okay, if there's one vertex going to both vertex D and also vertex C, we want to expand from the vertex that has the shortest path to a destination, because that's how greedy algorithms work. Okay, we're trying to be optimistic here. I think they really should call greedy algorithms optimistic algorithms, because it's actually more of an attribute of being optimistic than it is about greedy. But the term greedy algorithm is already used, in literature, so it is at this point it is difficult to change that. All right. So given what we know at this point, from D to E, from D to a destination, the length of the path is 4. From C at this point, okay, to a destination, that the currently known shortest path has a length of 10. So naturally, we're going to pick D to expand first, right? So to do that, we are ignoring, so we're going to have to remove that from Q. So Q is going to end up with a value of just, let's see, which one are we picking? We're picking D first, right? So, so that means C is the only thing remaining in Q. And then variable V is going to be whatever we chose, which is vertex D. Right. Yes. There we go. And then E is not known at this point. W is not known at this point. E prime is the same as before. L is the same as before. So that is representing all the things that we do before we get to the conditional the for each statement. So now we're getting to the for each statement. I'm just going to point out what we are talking about. So now we're getting to this for each statement here. We have already updated Q so that whatever we have chosen as a vertex to expand is no longer in Q. In other words, I just picked one thing from the boundary of expansion and say, let's focus on this one here. This one looks kind of promising. Let's figure out what edges would go to that specific vertex. So now we are looking at all the incoming edges to vertex D. So let me show the graph here. So this is vertex D. It's the value of the current variable V. So we are looking at two incoming edges. One is from C to D, the other one is from B to D. Once again, the order does not matter in this case. Okay, when we are looking at all the incoming edges to whatever vertex is in variable V, the ordering does not matter. So I'll just go ahead and say, let's take a look at BD first. Okay, so now we're going to take a look at BD. All right. So I'm just copying and pasting stuff here. Okay, just replace certain things. So we're looking at BD at this point, and vertex B is now in the variable W. So we are going to do the same thing. Okay, now we are asking this question. Okay, from the perspective of vertex B, we now have a new path to a destination. What new path are we talking about? Well, we pick D because D was in set Q, which means it has at least one path to the destination. Since B and D are connected by an edge, that means B also now has a alternative path, possibly alternative path to a destination. So the question is does this path have is it shorter than the path that is currently known going from vertex B to a destination? That is the question that we're asking. And the way we answer the question is to say, okay, what is L of D at this point? Because L of D is representing the length of the currently known shortest path from vertex D to a destination. That is 4. And then we have to add to 4 the distance of the edge of BD itself. So when you look at the graph, okay, right here, BD has a distance of 10. So we are looking at 10 plus 4, which is 14. So 14 is on the left-hand side of the less than operator. And then on the right-hand side, we are looking at L of B, which is the length of the shortest path at this point from vertex B to a destination. So we look up the L function, and currently we say the length of the shortest path from B to a destination is infinity. So the question really boils down to, is 14 less than infinity? I would think so, right? So now we're going to say, all right, since the condition is true, now we have to perform the 4 steps that are inside the conditional statement. All right, so then we got some questions here. Why we set non-destinations as infinity makes more sense now. Okay, cool. It's nice when things start to make sense, right? All right, so what we're going to do now is to update a bunch of stuff, okay? So what stuff are we updating? Well, we're going to borrow this, and then we'll make some changes to it. We know that Q is only C at this point. And we also know, okay, the rest are still okay. So the first thing we do is we update the L value of B to be the value that we just computed. In other words, we just found that the length of the new path is shorter than the path that we have known at this point, up to this point. So we're going to have to update the length of the shortest path to 14 from B to a destination. Now we have just found a path of a length of 14. Now, is that really absolutely the shortest path? We don't know yet, okay? But at this point, it seems to be the shortest. But later on, we might find, hey, there's actually a better way to do it. Then we'll update it later. But we also have to remember to update E prime there's no edge in E prime. Okay, this column is E prime. So there's nothing in E prime that is starting with B. So we have nothing to remove. And we will just go ahead and instead, add that new edge, which is going from B to D into E prime. And then after that, we also want to add B to the set of Q because now vertex B is on that boundary of expansion because we just touched it. Okay, so we just touched it. It is now on the boundary. All right, and Wade is typing something in the text channel. I'm going to wait a little bit. But once again, you guys can focus on this side of the screen. In an actual implementation, would you just use the max value for whatever data type yours is working with? Didn't catch it if this was already brought up. The answer is yes, infinity is a value. Okay, I know some of you are not believing me, so, which is okay. I mean, that's critical thinking right there, okay? Because you're just saying, I cannot, believe that until I see it, okay? So we just have to look up double infinity in C++, okay? So there you go. So infinity is an actual macro that you can use to refer to the value of infinity. So right here. So once you include math.h, this is actually a macro that you can use to specify the bit pattern that is actually being used to represent infinity. Now, infinity is not really a value, okay? It's more like a concept, but it does exist, okay? And in programming, nothing can be more than infinity when you're comparing doubles. So there you go. Yep, it is actually quite useful. I believe the same concept also exists in all scripting languages. They may not be called infinity or uppercase, but you just have to look up, how to specify the value of infinity. So anything that makes use of the IEEE double precision floating point number format would have a way to represent the bit pattern for infinity. There's another one for negative infinity, and there's also another one called not a number, NaN, N-A-N. So it's kind of interesting. All right, so getting back to the algorithm. Yeah, I keep digressing to stuff. Okay. All right, so we are now done with the edge BD. Okay, getting back to the graph. So BD is one edge, where we end up at vertex D. But another edge that ends with vertex D is the edge CD. So this is where things get a little bit interesting because we found a path from C to a destination already. Namely, it was CE. Okay. But now we are looking at, hey, guess what? There's another path now going from vertex C to vertex E. So now things are getting a little bit more interesting because the old L value from C to E was 10. Now it is 2 plus 4. So now we're asking, is 2 plus 4, which is 6, less than 10? The answer is yes, it is. So that means we are going in to update a bunch of stuff again because this condition turns out to be true. So now we have all 4 things that we need to do over here. And this time it's going to be a little bit more interesting. Okay, so we'll go ahead and specify a few things first. So this time the edge that is in question. Oh, okay, not this. I have to copy this first. There we go. So this time the edge in question is the edge CD. And C is again, using where vertex C is now the value of variable W here. So first of all, I just want to make sure that you guys understand exactly where we are in the algorithm and what the values are for each variable in the algorithm. Are we good so far? All right. All right, so now we know the condition is true, which means we have a bunch of stuff to update. The first thing we update is, oh, guess what? We just found a new path from vertex C to a destination, and it is now shorter. This new path has is shorter compared to the previous path that we have found, which has a length of 10. Now we have just discovered a path with a length of 6. So we update this, we update the L value of C, of vertex C from 10 to 6. That's the first thing we do. The second thing we do is to look up in E prime. Okay, so this is E prime. So we look up in E prime and ask, do we have any edge starting from C? Because that is no longer accurate. Okay, because in order for C to get to a destination, that path is no longer working. So now we say, yeah, we actually did have a record of in order to go from C to a destination, let's go through vertex E. That is no longer the shortest path. Now the shortest path is for C to go through vertex D to get to a destination. So that has to be, it's first removed and then we add CD as an edge. Okay, so I just did something lazy by replacing CE with CD, but technically speaking, we are performing two operations. The first one is to take out the edge CE from the set of E prime. The second one is to add the edge of CD into E prime. So are we good so far? Does everybody understand what I just mentioned? We are combining two steps into one when we're looking at the trace here. All right, cool. And we're going to add C to Q, but since Q is a set, we're not going to do something like this because you cannot have duplicate values in a set. So since C is already in Q, we are all good here. We don't have to update Q, or it would appear that the value of Q did not change because we're just adding C into a set that already has C as an element. Alright, so we are now done with the for each loop because we have explored all the incoming edges to vertex D in this case. So now we're getting back to the while loop. The while loop is going to take a look at Q as a set and ask, is it empty? Well, no, it's not empty. So we cannot exit the loop. Okay, the while loop, we cannot exit the while loop yet. So now we can look at the two elements in Q and ask, okay, which one has the least L value? Now, if you have two with exactly the same and they're both the lowest value, just randomly pick one. But in this case, it's not going to be like that because L of C is 6, L of B is 14. So the optimistic algorithm says, oh, I just want to be optimistic. Okay, let's go ahead and look at all the incoming edges to vertex C at this point. So now we have picked out, what vertex we want to expand. So now we just have to, I'm just looking for the right row to copy and paste. I believe it is, well, okay, I tried not to be lazy this time. Okay. So we are choosing vertex C. So vertex C is going to be removed from set Q, and instead it is now the value, vertex C is now the value of variable V, and then the rest we do not know, okay, because we are not quite at that point yet. So this is the edge, this is W, this is E prime, and this is L itself. Okay, so we are now done with let me show you what the algorithm, which part of the algorithm we are done. We are now done with this select V in Q and also the update of Q because V has to be removed. Otherwise, you end up with an infinite loop. So now we want to look at all the incoming edges to vertex C. So the best way to look at that is a diagram. So our focus now is, let's look at all the incoming edges to vertex C, and we have two incoming edges. One is coming from B, the other one is coming from A. Once again, the order does not really matter. So I'm just going to look at BC first, and then we'll look at AC. Alrighty. So let's take a look at what's going to happen now. So the first one is, okay, let me, alright, so I'm just not going to be lazy here. This is Q, this is V, and this is E. Okay, so we are looking at BC first. Alright, so we're looking at BC, which means B is going to be in variable W. And then the rest is, okay, let's go ahead and answer the question. are we finding a shorter path from vertex B to a destination at this point? Well, let's find out what it is right now. Okay, let's find out what is the length of the shortest path from B to a destination. According to the L function, it has a length of 14. Okay, so now the question is, what about C? What is the length of the shortest path from C to a destination? That turns out to be 6. And what is the distance from B to C? Okay, let's take a look. The distance from B to C is also 6. So that means I have just discovered a new path from vertex B to a destination, and that path turns out to be shorter than what I thought was the shortest path. Okay, it's because what I thought was the shortest path is going from B to C, and then from, oops, take it back. Let's see, B has 14, which is BDE. Yep, okay, that's right. Okay, so how do we know it's BDE? Because it is in E prime. It's in E prime. You can see how E prime has BD as an edge and then DE also as an edge. So when you look at E prime and you ask how can we go from B to the only destination E prime, that would be the only path. Okay, very good. Thank you. All right, so that turns out not to be the shortest path, okay, because this is one path with a length of 14, but guess what? This one is shorter, going from B to C and then back to D and then to E. That turns out to be shorter because that path has a length of 12. There we go. All right, so we're going to have to update a bunch of stuff now that we have discovered a new and shorter path. So when we update a bunch of stuff, the first thing Q needs to be updated. Okay, let me do this. It's not as easy when I do it in Joplin because usually I do this using a spreadsheet program, which is a little bit easier to work with. But using Joplin, it's harder for me to align things on the left-hand side because it's not actually a table. All right, but that's okay. I can still work with this. All right, the first thing is the length of the shortest path from B to a destination is no longer having a length of 14. It is now having a length of 12. So we update the L value first. And then we go into E prime. Okay, we look at E prime and say, do we have any edge starting with B? Because we have just found a shorter path. So we're going to have to alter where we go from B to the new path, right? So since we already have BD stored here, we're going to have to remove BD first. Okay, so the exact steps according to the algorithm is we have to remove BD as an edge, and then we're going to add BC as a new edge back into E prime as a set of edges. Okay, and then we're going to have to update Q because we want to add we want to add B back into the set. Since the set already has B in it, adding B to Q is not going to cause any actual update of the value of Q because Q already has element vertex B in it. So that concludes one iteration of the for each loop. Now we look at the graph again and we ask, what is the other edge going into vertex C? So that turns out to be vertex AC. That turns out to be the edge AC. And we're going to ask the same question. Okay, are we discovering a shorter path from vertex A to a destination? Now this time is a very easy answer because vertex A, okay, according to the L value of A, it is still infinity. Yes, we just found a quote-unquote shorter path from vertex A to a destination. And that turns out to be 8 plus the L value of C. The L value of C is 6, so 8 plus 6 is 14. So now we do a bunch of updates again. And let's see, where am I in terms of the cursor? There we go. There you go. So I just copied the new line. And the first thing we do is to update the L value. The L value is the new L value of A is the current L value of okay, I need to change a few things first. Sorry about that. Okay, so the first thing we do is we update what edge we are looking at. So now we are looking at the edge AC, so that vertex A is now the value of variable W. Now we go update a bunch of stuff. So the first thing we update is the L value of A, which is the sum of the distance of the edge AC, which is 8, and the L value of C, and the L value of C is 6. So we have 8 plus 6, which is 14. We computed this a little bit earlier. Can I scroll down? Yep, there you go. The left side is hard to read. Yes, it is. Oh, okay, cool. I did not know that you can do all the centering and fancy stuff. Well, I wish, as I scroll, the header would still display up here. I guess there's no easy way to make that happen. Maybe with some of you knowing all the cool stuff of CSS, you can do that. All right, so getting back to this. Yeah, that would be cool. All right, so back to here. We don't have any edge in E prime that starts with vertex A, so there's nothing to remove. But we're going to have to add the new edge, which is AC into E prime, because this edge is what is taking us from vertex A to a path that will eventually lead us to the destination. Now, is it the shortest path? Maybe, maybe not. Okay, we'll find out. And then we're going to have to add vertex A to the set Q because we just touched this vertex. Basically, whenever you update the L value of a vertex, you throw that vertex into the set Q. Because you just updated the L value, which means anything that goes to that vertex potentially might have a new and shorter path to be found. And that's why we add vertices into Q at this point of the algorithm. So I hope that kind of explains it, because it's one thing to look at the algorithm and know mechanically what we are doing. It's an entirely different thing to understand why we are doing it. Okay, what are the connections between all the statements? How do they get things done collectively? That is a different question. All right, so now let me go back to show the graph again. We are now done with looking at all the incoming edges into vertex C. So we are done with the for each loop. We're going back to the while loop. The while loop is going to look at the value of Q and say, well, is it empty? No, it's not empty yet. That means we cannot terminate the outermost while loop, which also means now we have to look at the elements in Q and find the one that has the least L value, okay, because we are using the optimistic approach. So according to that optimistic approach, between A and B, A has an L value of 14, B has an L value of 12. So we're going to pick B. All right, so we'll go ahead and pick vertex B. Okay, I'm just going to type the whole thing here, which also means we're going to have to remove B from the set. So the set Q only has A remaining, and then B is the vertex that we are removing from Q, so that it becomes the value of vertex V, of variable V, sorry. It is vertex B that becomes the value of variable V. And then the rest are the same. We're not changing anything else. But then we're going to have to go through the for each loop and find out what are the incoming edges to B. Okay, so here's the graph. So B turns out to be pretty easy to process because we only got one edge going from A to B. Okay, cool, easy peasy. So now I have lost the cursor on, oh, okay, that's because I'm on a different screen and I still cannot find my cursor. Let me click first. There we go. So we are now going to explore the only incoming edge to vertex B, and that is coming from vertex A. So we are looking at the edge AB, and that will also make vertex A the value of W, because basically what W is from which vertex are we going to the vertex that is stored in variable V, which is here. So we are going from vertex A to vertex B like that. So now the question is, are we discovering a shorter path? Okay, so let's figure out the length of the new path. Okay, if we are to go through from A through B to a destination, what would be the length of that path? Well, the length of that path is going to be the sum of the distance of the edge AB and the length of the current known shortest path from B to a destination. So L of B is 12, and then when you look at the length of the path of the edge from A to B, it is 1. So we are looking at 1 plus 12, which is 13. So 13 would be the length of the new path from A through B to a destination. We are going to compare that to the length of the shortest known path up to this point, and we can just look it up. That turns out to be 14. 13 edges out 14 just by 1 unit, but it is still less than. So that means we have to go through the then portion of the conditional statement, which is these 4 things that we have to do. So I'm hoping by now you guys will be looking at this and go like, oh no, not that thing again. This is getting boring. Because thinking this is boring is actually a good thing. So Q only has one element left, which is just A by itself. So once again, we have to go through all the 4 things that we need to do, starting with changing the L value of vertex A in this case. It is going from 14 to 13. And then the second thing we need to do is to take out all the edges from A to whatever in E prime. So we have AC here because the previous path, okay, the path that we're going to update, that we're going to toss away, is going from A to C. So we're going to have to remove this. And then and then we're going to add the edge AB because the edge AB is leading us to a new path that turns out to be shorter than the one that we knew before. So now we are done with this. And then the last thing we need to do is to add vertex A to the set Q, but that results in no update, quote unquote, because set Q already has vertex A in it. So we're almost done, okay, because now we are done with the for each loop, and then we are back to the outer while loop. So in other words, we are now back to the while loop over here, which is asking the question, is Q empty or not? The answer is Q is not empty. So we have one last iteration to perform here. I know we are running out of time, but it won't take too long now. Okay, so now we say, let's remove vertex A from set Q, and then variable V is going to take on vertex A as its value, everything else being the same. Now we get to the for each loop. Okay, so we're almost there, but the for each loop is kind of interesting because we got one little thing to do, just not a whole lot. Okay, so the for each loop is asking us to evaluate all the incoming edges to the vertex specified by variable V. So when you look up variable V, it is vertex A. So we are looking at all the incoming edges to vertex A. Guess what? We got 1. Because we got 1 incoming edge to A from C. Okay, we're almost done. Almost. Not quite, but getting there. Okay, so now we're gonna say, okay, fine, let's deal with that. We're looking at vertex C to vertex A using the edge CA, which makes vertex C the originating vertex, the value of variable W. So C goes here. And now we're going to evaluate, okay, are we just finding a new path from vertex C to a destination? So that question is going to start with, let's find out what is L of A. L of A is 13 at this point. What is the length of the path from C to A? That turns out to be 0, which is perfectly okay. It just cannot go negative, but 0 is possible for the distance of an edge. Okay, so 0 plus 13 is just 13. Okay, that's cool. Now we have to compare that to the length of the shortest path from C to a destination. That would be L of C, which is 6. So now we go like, 13 is less than 6. No, that is false. So if that condition is false, okay, we are basically talking about this condition here. It is false, which means we did not find a shorter path from vertex C through A to a destination. That path turned out to be longer than the shortest path that we have found up to this point. Okay, not much to do, because now we don't have to update that whole bunch of stuff, and we are now back to the beginning of the while loop, and the while loop is once again asking, is Q empty? And just like you guys are asking, is the class done at this point? The answer is almost. Not quite, almost. So we are now done with this algorithm. Okay, so the entire algorithm is done, but the question is, what do we have in E prime? Okay, that is the next question, is what do we have in E prime? So we can see what is in E prime. We have all of these edges in E prime. We have A to B, we have B to C, we have C to D, and then we have D to E. But what is that representing, right? I mean, that's the question. Just because we know what the value is for something doesn't really mean automatically translate to knowing what that is really representing. And I just found that I have a missing close paren here. Oh no, wait, did I? I thought that there was a missing close paren somewhere. That's A13. Okay. All right. So we're looking at the edges here, and let's see. Yep. So let's take a look at what we have here as the solution. Okay. And this is gonna take. I'm gonna do something like this because I want to go back to this path here and do some labeling. Okay. And okay, we can do something like that, and then just remove anything other than E prime. So E prime, oops, E prime. E prime is this particular set. Get to the end of the set notation, delete. Huh, okay, that didn't work. Let me try one more time. D $sign. That worked. Okay, there we go. So you guys can focus on this side. So E prime is like this. Okay, so I'm gonna label all of these things. I haven't really learned all the fancy stuff, like how do I highlight a particular edge. Pretty sure there's a way to do it, but I'm not gonna do the fancy stuff. Instead, I'm just gonna put parentheses around a value indicating it is in E prime. Okay, so we know A, B is in E prime. Okay, so I'm just putting parentheses around 1. And it doesn't like it. It doesn't like having 1 in the parentheses. Huh. Okay, so that is interesting. I don't want to waste too much time to figure out how to do the notation here. I wonder if this would do anything. Nope. There we go. Okay, that seems intuitive, right? I mean, using using the minus for a thin line, and then using equal as the thick line. I just guessed. That was just a lucky guess. And then B to C. Where is it? BC is the 6th. Right there, last one. Yes, as I was saying, I'm just having fun with a toy, that's all. And then we have CD. So CD is right here. Okay. And then the last one is DE. So D is this one. All right. So, as I said, focus on the right-hand side. So we have these 4 edges here, and these 4 edges, they are representing edges of the path. Okay, let me rephrase that. These 4 edges are representing the edges of the shortest paths from every single vertex to a destination. So let's double check, okay? Let's start with E, which is a destination itself. Since it's already a destination, it doesn't make any sense to have edges going into a destination. Okay, so it doesn't make sense. From the perspective of vertex D, it only has one way to get to vertex D. So It doesn't have a choice. From vertex C's perspective, it has two ways to get to vertex E. It has one way which has a length of 6, the other one has a length of 10, even though it's one single edge. So it is correct. Okay, the two highlighted arrows do indicate combined as a path from vertex C to get to E in the shortest path. The same thing applies to B, because B actually has quite a few ways to get to vertex E. It can do the roundabout thing, right? And well, that won't be a path anymore, because remember, a path can only have one vertex appearing up to once. So, but it does have the other path, which is from B to D to E. That is not shorter, right? This turns out to be the shortest path from B to E. And then from vertex A, it also has multiple ways. It can go through C, A, C, D, E, but that is also actually a little bit longer, just by one unit, because now we can go from A to B to C, and then to D, and then to E, and that turns out to be the shortest path from vertex A to vertex E. So I hope this is okay. This is effective, showing you guys, how to trace the algorithm, not exactly step by step, but I basically merged several statements into one single row of update, because when you look at the updates here, one row is not representing the execution of just one statement, but there should be no confusion of which statements either, because those statements do not conflict with each other. So, and in fact, the ordering of many of those statements, can be arbitrary also. Okay. Yeah. You can probably go through the video. Okay, one thing you can also do is to try to work on the algorithm by yourself first, and then go through the video again to see how it was solved. I don't have a problem, exporting this document as a PDF so that you guys can have a copy. But it's the steps that are important, and also the rationale behind the steps. Why are we doing it over here? Why is this algorithm finding the actual shortest paths? So those are the kind of questions that you probably want to think about a little bit, just so that you have a better understanding, not only of mechanically what we are doing for each step, but how the steps relate to each other and how it can actually find the shortest path. There we go. And then Wade is typing. There we go. Yeah, I can do that. Let me file, because I can just print one single note, and that makes it kind of easy. So I'm gonna print to file. And then Jonathan. Okay, let me type first. Download that file first, and then I'll go back to the text channel thing. Let me see. Yeah, if you guys want to sign out, that's fine. I will post the PDF. But if you have any further questions, this is my office hour. Okay, this is why I put the office hour right after class, so that I won't get bothered, because everybody else is much more interested in getting dinner first instead of asking me questions. Yes, that's definitely my scheme of trying to avoid having to answer questions. Alright, so there we go. And I'm posting the PDF. There we go. Alright, so there we go. And now I'm getting back to Jonathan's question, which is, wow, this algorithm showed me that finding the shortest path for all other nodes isn't exactly that much more work. Yeah, it really is not. And it can also work with multiple destinations. That's the other thing that's really kind of cool about this approach, is all you're doing is to put all the destination vertices into Q to begin with. That's it. Okay, that's the only thing you have to do to make an algorithm to find, oh, I'm not interested in only one single destination. What if we have multiple destinations? Not a problem. Just make Q start with all the destination vertices, and that's it. It's basically a freebie. The efficiency is you do suffer a little bit, okay, depending on which. Okay, so from the other algorithm's perspective, starting with only one single vertex, ending with one single destination. So if those two are kind of quote unquote close together, then the unmodified Dijkstra's algorithm can complete fairly quickly because it only has to expand the circle um, until the two vertices are connected, and you can be sure that there's no uh, other shortest path. Okay, because Q in that case will also be empty. If that is the case. Um, right. So with this particular algorithm, it is guaranteed, okay, assuming all the vertices can reach at least one destination. So we can definitely tell that the complexity of the algorithm is at least big theta. Oh, okay, we are talking about the lower bound in this case. So this is big. Oh, what is it? Big omega, right? So this is big omega cardinality of V. That is the lower bound. Because assuming this is assuming all the vertices are reachable from a destination. But the worst case is not really all that bad either. The worst case is this is going to be the upper bound, which is big O. So the big O of this algorithm is the cardinality of E, because we are guaranteed that we won't be looking at an edge more than once. Okay, so let me say that one more time. We only got 3 people online, and we are guaranteed to only look at one edge once, up to once. Okay, some may never be looked at, but if we do look at an edge, we won't look at an edge twice, guaranteed. So now the question is, can you prove that an edge won't be looked at more than once? It'll be E. So let me just type it in the text channel. The big O, which is the upper bound, the big O notation is going to be the cardinality of E, and then the big omega, I'm just going to spell out omega, is going to be the cardinality of V. Let's see, can we... that's not necessarily right. I'm just going to do something like this. Because sometimes you can have, it's not usual, but sometimes you can potentially have more vertices than there are edges. So the big O, or the upper bound, is going to be that, and then the lower bound is going to be the min of that, right? So the big omega, which is the lower bound, is going to be the minimum between E and V, the cardinality thereof. Or something like that. I have to think about this a little bit, but it's not bad. We are not even looking at the product between the cardinalities of E and V. Yeah, I think so. I mean, that's kind of why I structured the class the way it is structured. Alrighty, cool. So if you guys have any questions, go ahead and type in the text channel, but I think I'm going to close the voice channel and the screen share, because I think, I got everything down already in terms of what I can show through the voice and also the screen share. All right, if I don't see you guys again, have a nice day, and I know some of you I'll see tomorrow in the assembly programming class, and that should be an interesting session tomorrow. Probably a bunch of people are going to complain.